Alrighty, everyone, welcome. Welcome to the series Mudd Talks, How Transformative Scientific Research Happens at Mudd with Professor Albert Dato. My name is Vanessa Chu, Assistant Director in the Office of Alumni and Parent Relations. We thank you for attending and we hope you and your family are safe and healthy during this time. This talk is being recorded and will be distributed along with any presentation materials after the event. Please feel free to type your questions in Q&A, not the chat, and we will try to get through as many questions as we can after the presentation. Now, to briefly introduce our speaker, Albert Dato is the Associate Professor of Engineering at Harvey Mudd College, and he directs the Energy and Nanomaterials Lab, which focuses on developing solutions to energy and environmental challenges through the synthesis and applications of advanced materials. Driven by his passions for teaching, scientific research, and increasing diversity in STEM, he joined the faculty of HMC in 2014. I now turn it over to you, Albert. Take it away.
Thank you very much for the very nice introduction, Vanessa. I'm going to now share my screen. All right. Hello, everyone. Welcome to my talk. Thank you for being here today. It's such an honor to give this presentation to you and to give a Mudd talk. I'm Albert Dato. I'm an associate professor in the Department of Engineering here at Harvey Mudd College. And I'm really excited to tell you about how transformative scientific research happens at Mudd. Now, to get my talk started, I'm going to get started with a meme. So my students know that I love incorporating memes into my lectures, and I'm going to incorporate a meme into this talk. So there's a meme that popped up late last year. Here's an article in Fast Company. It's the how it started versus how it's going meme. And if you're not familiar with this meme, I'm going to give you a few examples just so you get an idea of how it works. So in October 2020, Joe Biden was on the campaign trail, and his wife, Dr. Jill Biden, tweeted out how it started versus how it's going. How it started, the picture on the left, you see Jill and Joe Biden at the start of their relationship, and then how it's going. So in October, they were on the campaign trail together when they were running for president. Sports Center, if you're into sports, tweeted out how it started for LeBron James, and on the picture on the left is LeBron James as a rookie. And the picture on the right is how it's going. That's LeBron James as a Lakers staring at all of his championship trophies and MVP trophies and everything that he accomplished in his 17-year career. Now, even astronauts got in on the meme. This is Thomas Pesquet of the European Space Agency. On the left, it's how it started. This is Thomas in his cardboard rocket ship. And then how it's going. It's Thomas as an astronaut in an actual rocket ship going to the space station. Paddington Bear, even fictional characters got into the how it started versus how it's going meme. On the left, you see Paddington Bear. He started out as an orphan. And then on the right, how it's going, this is Paddington Bear with his family at the end of the movie. So I hope you're familiar with the how it started versus how it's going meme. I like it a lot. And in this talk, I'm excited to just announce that we are at the start of something great. 1 year ago, Harvey Mudd College and I received a National Science Foundation career grant to conduct research into graphene-based nanocomposites. So if how it started versus how it's going is still a theme in several years, it is my goal to tweet something like this out. So this is going to be how it started, how it's going in 2027. Let me go over each of these things that I visualized. The research that we're conducting at Mudd, if all goes well and we meet our research goals, the students and I will advance knowledge in material science. In particular, we seek to transform knowledge of this material called graphene, which I'm going to spend a lot of time talking about in this presentation. And we not only seek to advance knowledge in material science, but we also seek to advance the manufacturing of advanced nanocomposites. We want to make possible the manufacturing of strong, lightweight composites with enhanced mechanical, thermal, and electrical properties. And we want to do it in a sustainable manner. So if we achieve these goals, this is going to be the societal impact of this project. We envision cars with a high strength to weight ratio, meaning they're very strong, but yet they're very light. This will enable cars to go longer between charges or tank fill-ups. And it will also be safer for the passengers because we envision enhanced crashworthiness for these vehicles. We also envision aircraft that are also capable of going further just because they're stronger, but yet they're lighter. But because we're going for multifunctional nanocomposites, we also envision enhancing the lightning strike protection of aircraft, as well as the ability of these aircraft to generate heat so they could de-ice in cold weather, such as the one that we're having in Texas right now. Also, in terms of renewable energy, we envision the nanocomposites that we're researching in our lab being used in wind turbine blades. If we could somehow make wind turbine blades bigger, but yet lighter, we'll be able to generate more renewable energy. And with electronic devices, high performance electronic devices generate a lot of heat, and yet they also need a lot of protection. So the nanocomposites that we're researching in the Energy Nanomaterials Lab here at Harvey Mudd College, we envision these nanocomposites being used in electronic devices and to protect them from impacts and as well as to dissipate heat. So this is what I hope to tweet out in 2027, how it started versus how it's going. But this talk is not about the future. This talk is about how we got here. This talk about how it's going right now. We have this National Science Foundation Career Grant, and this talk will start in 2014. So this is how it started, how it's going. So it is February 17th, and 2 days from now is going to be February 19th. It's going to be 7 years to the day that I stood in the Shanahan Auditorium, and I gave a talk, Graphene, History, Synthesis, and Nanotechnology. This is the talk that I was giving when I was being interviewed for this position at Mudd. So with me actually sitting here and giving this talk, I think things went pretty well. But you can actually watch this engineering seminar still. It's posted on the engineering website. If you go on engineering seminar and look at February 19, 2014, my talk is still there. And I gave this talk, I focused on graphene, the history, synthesis, and nanotechnology. So what you see here is an actual picture of graphene. These blurry white spheres that you see here are actual carbon atoms, and you can see they're arranged in this hexagonal pattern. So those are actual carbon atoms in white. And for those of you who are not familiar with graphene, that's totally okay. I like to start by talking about pencils. So most of you attending this talk have most likely used the pencil. You've taken this pencil, you probably sharpened it, and then you took a piece of paper and you started writing on it using that pencil. So I like to start at a place that everybody knows. So if you take a look at a pencil and you take a look at the dark pencil trace that it leaves on a piece of paper, if we were to zoom in on that, it would look sort of like this. So your pencil tip is made out of graphite, and these graphite plates that you see here are weakly bonded to each other through secondary forces. And when you write on a piece of paper, you're going to deposit all these graphite plates all over your paper. And if we were to focus on just one of these platelets that you see right here, and we were to say, look at it at the atomic level, we would see that it consists of dozens, if not hundreds, of these single atom thick sheets of carbon atoms arranged in this sp2 bonding configuration. So if we were to isolate just one of these sheets, one of these one atom thick layers in graphite, and that is simply what graphene is. Now, graphene is a wonder material. Graphene is the strongest material ever tested. It has an extremely high thermal conductivity. It has remarkable electron mobility. So graphene has these amazing mechanical, thermal, and electrical properties. And it's been under our noses for as long as humans have been using pencils. So if you want to isolate a single layer of graphite, one thing you could do is you could just take Scotch tape and you can continue to peel graphite with Scotch tape. It's called the micromechanical cleavage method. And if you peel it enough times, eventually you're going to wind up with a single layer of graphene. That's what got two researchers the Nobel Prize in physics. They were able to isolate graphene using this method and study its properties and started this thing called the graphene gold rush. Now, if you want to use graphene in practical applications, there needs to be a way to produce more of it, much more than peeling graphite with Scotch tape can produce. And there are actually methods out there right now. One way is to take graphite, subject it to a chemical treatment, and oxidize it. So when you oxidize graphite, you get graphite oxide. And when you have oxygen on individual sheets, they readily exfoliate. It's really easy to isolate a single sheet of graphene oxide, or GO. That's what you see right here. Now, if you subject the graphene oxide to an additional chemical treatment, you can get reduced graphene oxide. So that's what you get right here. So that's how you can get a single layer of graphite through this chemical method. The other method is called liquid phase exfoliation. You take graphite, you put it into a certain liquid where the molecules can get in between the graphene planes. And when you use the right chemicals, you could actually gently exfoliate and obtain individual graphene sheets. So the methods that you see here are called top-down methods of graphene production. You're taking graphite and you're breaking it down to a single layer of carbon atoms. This is called the top-down methods. Now, when I gave my seminar several years ago, I went over these methods, but then I went into the method that I discovered of producing graphene. So when I was a graduate student, the very first paper that I published was titled Substrate-Free Gas Phase Synthesis of Graphene Sheets. So far, it's at 583 citations and counting. If it wasn't for this paper, I probably wouldn't be sitting here today giving this wonderful talk to you. But what I reported in this paper was this method that I discovered. So as a graduate student, while I was working in the lab, I found out that if you take pure alcohol, 99.9% alcohol, and when I say alcohol, I mean drinking alcohol. So if any of you have had vodka, vodka is 40% alcohol, 60% water. I was working with 99.9% alcohol. And what I was doing was I was sending this alcohol into an atmospheric pressure microwave generated plasma. So all a plasma is it's a gas, but then you also have the gas ions and free electrons. So in this case, I was working with argon gas and I was generating an argon plasma. So this argon plasma consisted of argon neutrals, argon ions, and free electrons. The free electrons absorbed energy from the applied microwave. So I was using a microwave with a magnetron similar to what you have in your microwave oven. So I was generating an atmospheric argon plasma. And I discovered that when you shoot pure alcohol into a plasma, the plasma breaks apart ethanol. So ethanol is CH3CH2OH. It breaks it apart. And then the carbon atoms that exit the plasma reform into single layers of graphene. So this is what I discovered as a graduate student. So this is the substrate-free gas phase synthesis method. So I was able to create graphene without graphite. So this is called a bottom-up process where you start from the bottom and then end up with a graphene sheet. Now, this method has a number of advantages over top-down methods. If we look at top-down methods, if you want to obtain a single layer of graphene from graphite using either liquid phase exfoliation or the Hummer's method, this oxidation exfoliation, you're going to need a lot of chemicals such as nitric acid, sulfuric acid, hydrazine, sodium hydroxide, hydrochloric acid, and you're also going to need a lot of purified water. So if you want to generate a lot of graphene by this method, you're also going to be generating a lot of chemical waste, and you're also going to be using a lot of water. Now, when you take alcohol and you shoot it into a plasma, number one, you can generate alcohol from renewable resources. And you can also power a plasma reactor using renewable energy, such as solar and wind. Now, when you do that, and you send alcohol into a plasma, you wind up with graphene. So that's that black powder that you see in the vial. But the byproducts of this process are hydrogen gas and carbon monoxide. You can capture the graphene, and you can also capture and reuse the exhaust gases in this process. So relative to top-down methods, the gas phase synthesis process is a lot more sustainable. The other advantage to the gas phase method, so this is gas phase synthesized graphene. We're going to call it GSG from here on out. What you see on the left is reduced graphene oxide. This is graphene that you obtain from graphite. Anything that you see here in yellow, those are actually holes in the sheet. And anything in gray are these defects in the sheet itself. Anything that's pink or green or blue, these are contaminants that wind up contaminating the graphene during the oxidation process and exfoliation process. Furthermore, reduced graphene oxide is 86% carbon by mass, so it also has oxygen. It's not a pure carbon material. What's great about GSG is that it's a highly ordered material, as you can see here in the transmission electron microscope image on the right. It doesn't have the holes or the defects. And it's also 99% carbon by mass. So it's close to an ideal of a graphene sheet that you can get. So that's what I presented to the students during my talk in 2014. I was telling them all about gas-phase synthesized graphene and how I discovered it. But then if you somehow, for some reason, watch this talk, it was a 50-minute talk, but it actually gets cut off at 35 minutes. And that was by my request. So I took a risk with my interview, and I asked the engineering department, hey, could you please cut off my video at the 35-minute mark? Because what I wanted to go over in my talk is what I wanted to do at Harvey Mudd College with the students. So when the video cut off, I looked at the students and I said, look, we're making gas-phase synthesized graphene. Let's put it into these polymers and let's create multifunctional composites that have high strength and high thermal conductivity and high electrical conductivity. And so basically the vision that I have for 2027 is what I pitched to the students back in 2014. And because I was really excited to come to Harvey Mudd College and potentially do this work with the students. So a few hours after I gave this talk, I hopped back on my plane, went back to the Bay Area, because I went back to work. I interviewed with another institution a week later, but then a few weeks went by and really my hopes of getting this job started to, fade with time. So I already accepted the fact that I wasn't getting this job. And then I get this weird phone call out of the blue in the middle of the day from a phone number that I don't recognize. And I answer the phone, and on the other end was Professor Dato, who was chair of the Department of Engineering in 2014. He's also a Mudd alum. He graduated in 1981. And he pretty much told me, Albert, you are the top candidate out of all the candidates that we have. Would you join us here at Harvey Mudd College? We'd like to offer you a position. And that was quite possibly one of the happiest days of my life. My heart almost jumped out of my chest. And I told him, I was like, yeah, this is something I really want to do. And then came the all-important question that gets asked when you get an academic position. It's like, all right, well, what do you need to get started? You gave a good talk about your research. What do you need to get started? And this was the time that I had to be really honest with Z. I said, Z, if I were to bring a research program where we make graphene and we develop graphene applications at Harvey Mudd College, I'm going to need this much money. We're going to need this much money to buy a plasma reactor. We're going to need this much money for supplies. We're going to need this much money for chemicals and reagents and argon gas and all this stuff. And so I threw a number at him, and that number was met with pretty much like 15 seconds of silence. And then he said, you realize we're not a research institution, right? And I said, yes, I realize that. And but this is really what we need to get started. Any less than this, and I don't see the research happening. And I told them I also need a lab. I envision doing research with the students, doing research together with the students, discovering new things. So I'm going to need a big enough lab to do this. I can't do this work in a closet. So Dato pretty much said, okay, let me see what I could do. And I'm so grateful that a few days later, Professor Jeff Groves, who was dean of the faculty at the time in 2014, and Professor Dato came back, and they gave me a startup package that was really, really tough to refuse. And I'm totally grateful that they made that investment in me. So here's lesson number one. Transformative scientific research happens at Mudd because the college invests in the faculty. The college made a big investment in me. They took a big chance with me, and I'm thankful that they did. And thanks to that initial investment, we're currently where we are right now. Now, I got the job, and then July of 2014, that was my first day of work on July 1st. And I remember coming to campus, and the first place that I visited was my lab. So if you're ever on Harvey Mudd College campus, please come to Parsons 2387. Parsons 2387 is my lab. We're happy to have you. I'd be happy to show you everything that we have. But this was the picture that I took on my first day of work here at Harvey Mudd. It was this empty lab, and I remember looking around going, wow, we could really do things in this lab. I was really excited. But it was, it was time to put up or shut up. It was Albert, get your research program started. So here's reason number 2, why transformative scientific research happens here. It happens because faculty and students can explore new areas of research together. So when I came to Mudd, I must admit that I was an expert at making graphene using plasmas. I made other materials using plasmas, and when I was a process development engineer in industry, I was depositing silicon dioxide on silicon wafers using high density plasmas. So I had some knowledge and some expertise on how to do that. But I had zero knowledge and zero expertise in making graphene-based nanocomposites. This was a completely new area for me. And this is where Nicole Subler comes in. In the fall of 2014, I sent out a call for researchers. And the first student to apply to my lab was Nicole Subler, HMC Engineering, class of 2016. And during the interview, I was really excited that she applied to my lab. She was the top student in my Engineering 86 Materials Engineering course. And during the interview, I was upfront with Nicole. I said, look, Nicole, I envision a nanocomposites research program here at Harvey Mudd College. However, I'm just starting out on this journey. It's going to be an adventure. Will you join me? We're going to be doing this together. We're going to get this thing started. And Nicole was so excited to get started with the lab. And the way I run things in my lab is I like to give students full ownership of the research project. So I told Nicole, I said, look, here we are, we're at point A. We don't have a nanocomposites research program. Point B, I envision in a year, we have a method of making nanocomposites reproducibly, repeatably, and we're studying their properties. I'm going to give you the keys to the car. If this research program is a car, I'm giving you the keys to the car. You're going to drive this project. I'm going to sit in the passenger side. I'm going to give you support. I'm going to give you advice. I'm going to give you mentorship, but you have full control of this project. You just tell me what you need. And this is an experience that I like to give to my students at Harvey Mudd College. It's when I was a graduate student at Berkeley, my research advisor pretty much was the same way with me. He trusted me. He gave me full control of the project, and we wound up discovering something great. And Harvey Mudd College students are just such amazing human beings, so driven, so passionate, so concerned about the impact of their work on society. And I had full confidence that if I gave Nicole this project, that it would be successful. So I gave Nicole the keys to the car. I had her drive the project, and over a span of the year, she got to it. I mean, she dove into the graphene-based nanocomposites literature. She looked at how other labs were making graphene-based nanocomposites, and she took that, and based on what she learned, she started developing her own methods of making these nanocomposites. So what you see here is a picture of Nicole. She's actually making a mold out of silicone. So this is this purple silicone mold that she's holding that we use to fabricate the composites. So she figured out how to make molds and how to treat them so that we minimize the bubbles. She also learned how to mix the nanomaterials with the epoxy resins and get a nice uniform dispersion of these and actually put them into these silicone molds. So what you see here is Nicole making these dog bone shaped specimens. And I'm going to go over these a little bit later on in this presentation. But Nicole figured out how to do this. And then she learned how to use the materials testing system that we have in the basement of Parsons. And she conducted the materials tests on these specimens that she was fabricating. So within a span of a year, Nicole, working independently with minimal supervision, pretty much built the nanocomposites research program here at Harvey Mudd College. And in the span of a year, she developed this really simple method of taking nanomaterials, mixing them with polymer resin and polymer hardener, disperse them, mix them in a planetary mixer, degassing them, putting them into molds. So we had a nanocomposites research program in the end of the year. The bittersweet thing with Harvey Mudd College students. I love working with them. I love teaching them, but eventually they have to graduate and they have to go make their mark in the world and make an impact on society and do big things in academia and industry. So Nicole Subler graduated in 2016, but I'm thankful that she took Jacob Canego, who graduated in 2018, under her wing, showed Jacob how to make nanocomposites, pretty much passed the torch on to Jacob. And Jacob took the method, revised it, improved it, and eventually started doing his own tests. So there is a fateful day in 2017. So everyone in my lab has my cell phone number. They can contact me anytime, and I text with my students a lot. And on June 22nd, 2017, 4:44 p.m., Jacob texts me this. He said, "Testing is looking good. I don't have analysis, but an eyeball test. We're seeing 20 to 30% increase in ultimate tensile strength, or UTS." I remember reading this text message and going like, this is bonkers. This doesn't make any sense. I knew that graphene would strengthen the nanocomposites, but 20 to 30% was a little out there. But I was skeptical, but then I didn't want to say that by text message. So I said, great to hear. Can't wait to see the data. So the next day we sat down, and I just want to make sure everyone understands what Jacob did. So Jacob fabricated this nanocomposite specimen that you see here on the right. It's held in place by two grips, one on top and one on the bottom. And the way we test these materials is we pull them apart at a constant rate, and the machine measures the force that is needed to pull the specimen apart at a constant rate. Now, that silver device that you see in the middle that's latched onto the specimen that says MTS on it, that's an extensometer. And what the extensometer does is it measures the elongation of the specimen. So we're able to get force versus elongation data. And you can convert force and elongation data to stress versus strain graphs. So Engineering 86 is materials engineering. It's a required course for the engineers here at Harvey Mudd College, but chemistry majors, physics majors, math majors, CS majors take the course as well. But by lecture 2 of the course, students understand exactly what this test is all about and the mechanical properties that you could determine from a stress versus strain curve that you see here. So these are the stress versus strain curves of pure epoxy. And what we're looking for here is the peak. So if you see a peak, that's its ultimate tensile strength. That's the UTS of the material. If you go to the linear region, that slope is your Young's modulus. It's related to the stiffness of the material. And students then can integrate the area under these stress versus strain curves using either Excel, MATLAB, or another piece of software. And the area under the curve is toughness. Now, we pull these specimens apart until they snap. So you see a vertical line, these vertical dashed lines that you see here, that's when it goes to zero force. That's when your specimen snaps. Now it takes zero force to pull the specimen apart at a constant rate. The location of the vertical line on the x-axis, that is your strain at break. That's how much your specimen stretched before it snapped. So these are the properties that we're looking for in these graphs. Now, when we run experiments in our lab, we like to compare our gas phase synthesized graphene with commercially available graphene derived from graphite. We want to make sure we get an apples to apples comparison with how the gas phase synthesized graphene is doing. So what Jacob did was he created nanocomposites containing 0.001 grams of graphene mixed with 1 gram of epoxy. That was the concentration. That was our 0.1 weight percent. And so what he did was he made these specimens and he tested them. And what we found was what we expected. What you see here is pretty much what's reported in literature. When you put some of this commercially available graphene derived from graphite into polymers, you're going to increase the strength, increase the stiffness of your material. However, the toughness doesn't increase much. And the reason why is because the strain at break drops when you start adding graphene into polymer. So this is the trade-off properties of materials. You want to make something stronger, it's going to come at the expense of something. And in this case, the expense is strain at break. You can't stretch these materials out longer than a pure epoxy specimen before they fracture. So this is what Jacob obtained, and it made a lot of sense to us. Now, Jacob discovered something astounding when he put the gas phase synthesized graphene into epoxy. So when he did that, 0.1% of gas phase synthesized graphene into epoxy, this is what Jacob discovered. So the green curves that you see here are the curves of stress versus strain curves of 0.001 grams of gas phase synthesized graphene and 1 gram of epoxy. We saw an increase in strength, an increase in stiffness, and an increase in toughness because the strain at break was higher. Specimens containing gas phase synthesized graphene were actually elongating longer than a pure epoxy specimen, than a specimen that didn't contain graphene. And not only that, it significantly increased the strength. So we were able to have our cake, which is increase in strength, and eat it too, which is increase in strain at break. This was a big aha moment. So this is what Jacob was texting me about on that fateful day in 2017. This was very interesting. So here's all the results side by side. Blue curves are the commercially available graphene-based nanocomposites. Green curves are GSG. Red curves for reference are pure epoxy that don't contain any graphene. As you can see, even the GSG outperforms the commercially available graphene at the same concentrations. And it's able to have a much longer strain at break. So this is the moment where we just sat there and we said, why? So one of my favorite memes on the internet is, it's not a very popular meme, but it's why though? Why though? It's one of my favorite memes because as scientists and as engineers, I always tell my students, you have to ask why. Something breaks in the lab, why did that happen? If you have a problem with your clinic project, why did that happen? If you discover something very interesting, like simultaneously increasing the strength, stiffness, and strain at break of a material, why did that happen? So Jacob had to graduate. And the answer to why though, the torch got passed to 3 students. Chance Biscara, HMC Engineering Class of 2019, Taylor Sloop, HMC Engineering Class of 2020, and Kevin Nakahara, HMC Engineering Class of 2020. So Jacob got to train them, show them how to make the nanocomposites. But what Chance and Taylor focused on was trying to answer the question why. Why were we getting simultaneous increases in strength and strain at break and toughness in these graphene-based nanocomposites? So they used this scanning electron microscope. So you see the scanning electron microscope right here. This is a scanning electron microscope that's jointly owned by Harvey Mudd College and Pomona College. It's located in Pomona College. So Chance and Taylor, they trained on it. And what they did was they focused on analyzing the fracture surfaces of the specimens that Jacob broke apart. They wanted to know if looking at the fracture surfaces can tell us something about what happened, why we got those results. So what you see here is an image that Chance and Taylor took of pure epoxy. So stress versus strain curve epoxy is on the left. And on the right, you see that the surface of this pure epoxy is relatively smooth. It has a smooth fracture surface, which means cracks easily propagate through the material. So epoxy is a cross-linked polymer. It's really strong, but it's also brittle. So when you're pulling it apart in a tensile testing machine, once cracks start to form, eventually you're going to get to this critical stress required for crack propagation. And once that crack starts to propagate, it moves through the material unimpeded, which results in this nice, smooth fracture surface that you see right here. So when Chance and Taylor took a look at the fracture surface of a nanocomposite containing graphene derived from graphite, they got a result that we expected. We saw a rough fracture surface. When you see a rough fracture surface on a scanning electron microscope, that indicates that cracks have a hard time moving through the material. They don't move through the material as easily. Matter of fact, the graphene reinforces the polymer, making it stronger. but they can also divert cracks. They could also bridge cracks. And that's the reason why you see an increase in strength in the stress versus strain curves. It's because it takes a lot more energy, a lot more stress to break apart a graphene-based nanocomposite specimen. So everything that you see here is what expected. But here's what Chance and Taylor saw when they looked at the nanocomposite with gas phase synthesized graphene, with GSG, a much rougher fracture surface. Cracks have a very hard time moving through a nanocomposite specimen containing gas phase synthesized graphene. It could be that the gas phase synthesized graphene is reinforcing the polymer really well. It could be that the gas phase synthesized graphene is dispersed really well. There's so many questions that were generated from this image alone. But bottom line, this is something that we observed, and it partially explained why we're seeing greater increases in strength in these gas phase synthesized graphene nanocomposites. Rougher fracture surface, harder crack propagation. So Kevin Nakahara took the lead in taking all of this data that we obtained over the years, and he took the lead and wrote the paper, Enhanced Mechanical Properties of Epoxy Matrix Nanocomposites Reinforced with Graphene Synthesized in Atmospheric Plasmas. It went into a very appropriate journal called Plasma Processes and Polymers. But this is a goal in our labs here at Harvey Mudd College. We want our students to publish their work in peer-reviewed scientific journals. That is always a goal, for them to do this and to also present their work at scientific conferences. And I'm really proud of this paper because it was just this team effort for students throughout the years. And here's lesson number 3. Transformative scientific research happens at Mudd because undergraduate students can make scientific discoveries through independent research in the laboratory. We have a pretty unique environment here at Harvey Mudd College. If an undergraduate student wants to conduct research at, say, a research institution, that undergraduate student is typically most likely working under a graduate student, and that graduate student's most likely working under a postdoctoral advisor or a research advisor. Here, the undergraduate students can make these discoveries independently. They can drive the projects, own the projects. And again, Harvey Mudd College students are some of the most brilliant, hardworking, driven students that I've ever met. And if you give them a project and get out of the way, results happen. So here's another reason why research happens at Mudd. If you download this paper and you go to the acknowledgements, you'll see that it says, this project was financially supported by the following funding sources at Harvey Mudd College: the Vandiver Experiential Learning Fund, the N. Sprague Third Summer Research Fund, the Engman Research and Experiential Learning Fund, and the Harvey Mudd College Student Philanthropy Campaign. Now, here's another reason. Transformative scientific research happens at Mudd because the college, alumni, donors, and trustees provide strong support for research and scholarly activity. The funding that you see here helped fund Jacob, Taylor, Nicole in their summer research. It helped provide them with summer stipends. It helped provide them with summer housing. And not only that, these internal funds give the students some money for supplies to carry out their research. This internal funding was so important to getting this paper published and to getting these spectacular results in the laboratory. Now, here's another reason why transformative scientific research happens at Mudd. We have amazing staff. So what you see here are just a few of the staff members that were involved in this project. There were so many people involved, but Sydney Torrey, Sue Lindley, Kim Pandolfo, Lorena Gonzalez, anytime we needed something for our research, they were there for us. They would help us obtain these materials or chemicals. And they would always help us out in the lab. Sam Abdul Mahdi, so valuable. Anytime something broke in the lab, or anytime we needed some gases, or anytime we needed something in the lab, Sam would be there to help us out. He really makes it happen. Willie Drake made sure that all the computing resources were there for us and were working. If the computer on the materials testing system was not acting right, he would help us out. He would help us install new equipment. I mean, these people that you see here are so important to research at Mudd. Penny Menisco She has such an important job here at Harvey Mudd College. She trains all the students in lab safety. She audits all of our labs to make sure everything is safe. She also provided Chance and Taylor with the scanning electron microscope training. Daniel Guerra in the chemistry department, he also helped us out obtaining personal protective equipment, as well as helping us dispose of our waste and also get some chemicals. The people that you see here are just a few of the many staff members that really help research happen here at Mudd. As a matter of fact, Vanessa is awesome because she's helping me just focus on my presentation right here. So transformative scientific research happens at Mudd because the staff enable students and faculty to focus on research, to focus on our work. And I'm so thankful that we have this amazing staff. So why though? Getting back to why though. So we got all these cool results in the lab. And my research advisor at Berkeley told me that good research answers questions. Great research generates even more questions. And the results that the students got in the lab actually generate a lot more questions than answers, because what we see here cannot be fully explained by our current understanding of graphene and graphene-based nanocomposites. There's something here, some mechanisms that are yet to be discovered. Now, with this data, I decided I'm going to go apply for a National Science Foundation Career Award. I would like to answer all of these questions. Why did this happen? And if you've ever submitted anything to the National Science Foundation, you're greeted with this website to submit proposals. But submitting a proposal is so much more than just saying, here's some cool stuff that I did in the lab. This is pretty cool results. Can you give me some money for my research? No, you actually have to answer some really important questions in a 15-page proposal. For example, you have to answer questions like, how will this project advance scientific knowledge? What is the intellectual merit of your work? How will this project benefit society? What are the broader impacts? How will this project assess success? Are you qualified to do this project? Do you have the facilities and equipment needed? And to what extent do the proposed activities suggest and explore creative, original, or potentially transformative concepts? I had to articulate this in a proposal. And this was me when I started writing my proposal. I did not know where to begin. I was stumped. I hit the worst writer's block of my life. I was frustrated. I was stressed out. How do I answer these questions? How do I articulate it? And these are where some really special people come in. Professor Lilia Hawkins in the chemistry department and Professor Nancy Lape in the engineering department, both of them obtained National Science Foundation Career Awards. And when I was starting out, they were so helpful. They just said, Albert, here's our proposal that got accepted. You feel free to use it, feel free to take a look at it and analyze it. Their proposals were so important in getting me started writing a career proposal. Now, Professor Lori Bassman and Professor Chris Clark in the engineering department, they've obtained National Science Foundation funding. They've served on panels. So they pretty much, they're very busy people, but yet they told me, Albert, give me a draft of your proposal. I'd be happy to give you feedback. I'd be happy to, give you my critique and help you get started. So I got so much support with my proposal from my colleagues. And transformative scientific research happens at Mudd because faculty support each other. Collaboration is our culture. I am thankful every day that I get to work with such amazing people. So this person gets a slide all for herself. This is Professor Elizabeth Orwen. She's chair of the engineering department here at Harvey Mudd. She's also a Mudd alum. She's HMC engineering class of 1995. Professor Orwen has been the chair of the department since I got here in 2014. And over the last several years, anything that I needed, whether it's something for teaching, whether it's a course that I wanted to teach, whether it's something for research, whether it's something for professional development, she always found a way to make it happen for me. And she's always supported me, and I've felt nothing but supported in this department. Thanks to Professor Orwen and my colleagues. But in 2018, the program to which I was applying was hosting a career proposal writing workshop. So this was in 2018. It was in the middle of the semester. It was in March. It was across the country. It was on the other side of the country in North Carolina. And I asked Liz Orwen, I said, Liz, there's this proposal writing workshop. I think it's really going to help. And without hesitating, she just said, Albert, go to this thing. We'll figure out a way to cover you in your courses. We'll pay for your airfare. We'll pay for your hotel. We want you to go meet your program director. And transformative scientific research happens at MUD because the college supports the professional development of the faculty. So I got to go to this career proposal writing workshop. I got to meet with the program director, to which I would submit my proposal face to face. Program director was able to take a look at my proposal, give me real-time advice, tell me that's a bad idea. You should put this in. That's a great idea. You should articulate this. I got this real-time feedback and all my questions answered about the proposal writing process. I also got to meet my colleagues, and I also got to learn how the National Science Foundation evaluates proposals. So I got such great insight into the proposal writing process by going to this workshop. And one of the things that I learned is to articulate the facilities and the equipment that you have. You want to show the National Science Foundation that you already have the infrastructure in place so that you can achieve success in your proposed research. So in my proposal, I articulated, look, we have all the equipment that I need. We have the tensile testers. This black box that you see right here measures the thermal conductivity of materials. The clinic program invested in an injection molder that you see here right in the middle. We have that scanning electron microscope. I have a plasma reactor. We have the personnel. So what you see here is you see Isabel Martos-Rapath and Pichai Alertvalai. These were the other students who were in my first group of researchers in my lab. But we have all this stuff. And transformative scientific research happens at MUD because we have the facilities and equipment for conducting research over here. And that's what I articulated. There was another thing that was really valuable for me personally and for a lot of my colleagues here at Harvey Mudd. In the summer of 2019 is when I really focused and when I wrote this winning proposal. And President Maria Clave, Dean of Faculty Lisa Sullivan, in concert with several members of the Board of Trustees, actually provided us with salary supplementation to conduct research in the summer of 2019. So normally we get internal funding for our students and we get about $1,000, which we could either use for a summer stipend or for supplies for the students. So typically that $1,000 goes towards the student to make sure that they could conduct the research in our lab. So faculty who conduct research at Harvey Mudd College during the summer are pretty much doing it for the love of it, because we really care about research and doing this research with the students. In the summer of 2019, we actually got a supplemental salary, and that actually enabled me to focus on mentoring the students in the lab and writing this proposal. I didn't have to go seek some consulting opportunities to make some additional funding during the summer. I got to just really focus. And again, I'm going to stress that transformative scientific research happens at MUD because the college, alumni, donors, and trustees provide strong support for research and scholarly activity. So you take everything that you find in the lab and you take all these reasons that I gave for you for why transformative research happens at MUD, and you put it into a proposal. And that is exactly how we received an NSF career grant for the nanocomposite research. We did it. This was a total team effort. I just had to articulate everything that happens at MUD, all these amazing things and the amazing students, facilities, and staff and colleagues that we have over here. And that's really how this NSF career grant happened. So in closing, I'm going to do some how it started, how it's going. And I just want to stress that these students would have wound up where they wound up, even if they didn't do research in my lab. I take zero credit for where these students wound up. I just want to just say how proud I am of them and just how thankful I am to have such high quality students join my research group. So after Nicole Subler graduated, she got a job in industry at Bolt Threads, did some big things there, and now she's working at a company called Promega. She's doing great in industry. Jacob Canego, after graduating from Harvey Mudd College, well, how's it going? Well, he went to Stanford, got a master's in material science and engineering, and is now working for a company called Synovia. Chance Biscara graduated, and he's now in Virginia Tech, getting a master's in mechanical engineering. And here he is, he's having such a great time in Virginia. Taylor Sloop, after graduating from Harvey Mudd, she is now in a PhD program in the School of Material Science and Engineering at Georgia Tech. She's doing some amazing research on steels and metals. Kevin Nakahara is now at Caltech. He's getting his PhD in mechanical engineering. I'm just immensely proud of these students. Now, terms of how it started, how it's going. On the left is how this research program started. These are the members of the lab that got everything going up to this point in time. And how it's going, there are new members of the lab. These 4 students have their work cut out for them. Our Pizza Bhutani, class of 2023, JT Griffin, class of 2023, Sean Wu, Sydney Chenevert, all class of 2023 students are now gonna answer the question, why though? Why are we seeing all of this stuff? So the questions that you see here are a few of the many questions that they're gonna have to answer, because this is what the National Science Foundation is funding. We wanna know if this enhancement in properties also happens in other polymers such as polyester, ABS, and PEEK. What are the strengthening mechanisms of GSG-based nanocomposites? What about increasing the volume, the mass fraction of gas-phase synthesized graphene in these composites? So they have a lot of work to do. And this nanocomposites project is just one of several projects that's going on at the Energy and Nanomaterials Lab at Harvey Mudd College. We're doing other things as well. We're still figuring out how to make graphene, how to make more of it using microwave plasmas. I have students working on easier plasma reactors such as RF plasmas to see if we can make materials that way. I have 2 students, McKenna Parkinson and Weston Miller. They're looking at ways that we could separate oil from water when water gets polluted with oil. Can we somehow do that with the materials that we make in my lab? Gordon Krause and I are working on a project where we're putting graphene into lubricating fluids to see if we could reduce the wear of moving parts. And we just recently published a paper on this. And I am so proud and so thankful that I've had these students that you see right here join my research group over the years. So these are the students that have been a part of Energy and Nanomaterials Lab. And again, I just seeing this slide brings me a lot of great joy. A lot of them are out doing big things now in either graduate school or industry. So I want to end this by saying that this talk just focused on me and the research that's going on in my lab. But I want to say that whatever transformative research I'm doing, multiply it by 100. There's so much research, fascinating, transformative research that's going on here by all the other faculty members at Harvey Mudd College. I'm just so thankful every day that I get to come to campus and I get to work with such amazing people who are passionate about teaching and who are also doing really big things in their research groups and in their laboratories. So a lot of us have external National Science Foundation funding, but a lot of the research that does get conducted at Harvey Mudd is a result of the internal funding that we receive from the college. So I just want to stress again, transformative scientific research happens at Mudd because the college, alumni, donors, and trustees provide strong support for research and scholarly activity. So this is how it started and this is how it's going. That's the story of this presentation. And this is what I hope to tweet out in 2027. Thank you for attending my talk. I'm happy to answer any questions.
All righty. If you have any questions, please put it in the Q&A and then we'd be more than happy to take your questions. Well, Albert, I do have a question for you.
Okay.
What is your favorite thing to teach your students?
Oh, the favorite thing to teach my students, definitely. It's really the relationships between the structure, the properties, the processing, and the performance of materials. I teach Engineering 86 and I also teach biomaterials. And it's just so exciting to be able to teach this to students, right? That when you bend a piece of metal, why is it bending, right? What is happening at the atomic level and how can we process this material to change it? Something as simple as bending a fork. So anytime I have a pre-frosh who has lunch with me at the Hawk, hopefully we get back to in-person in the fall. But one of the things I like to do with pre-frosh is I like to have them take a fork that's at the Hawk and then I give them permission to bend it. And I tell them, tell me exactly why that happened. And they go, I don't know. And I say, well, you know what, that's the first midterm in my course. So that's really one of my, that's my favorite thing to teach the students.
Great, thank you. Are you mixing in graphene with other polymers besides epoxy? What other sorts of materials are interesting to combine with GSG?
Yes, so that is the task of the next group of students coming in. So we have this work on epoxy. We tried some other materials in our lab, but COVID sort of cut things short. So we were getting these exciting results with epoxy, and I had a group of students last March who were getting ready to actually put it into ABS. So ABS is a widely used polymer, but it's an injection molded polymer. It's not a resin. So we were going to figure out ways to mix the GSG with the polymer resin and then injection mold these nanocomposite specimens. So we're going to be doing that. We're also looking at PEEK, which is also widely used in industry. We're also looking at polyester. So the next group of students coming in, I'm hoping they can get started on that kind of work.
Great, thank you. How competitive is it to get into your lab?
In terms of competitiveness, really it comes down to, in terms of summer research, it comes down to summer funding. And really what I'm looking for in students is the desire to be there, an excitement. Right, so that I take a look at their applications, and then if some of them are sitting there going like, graphene, I'm really crazy about graphene, or I really want to do something for the environment, or or I really want to investigate how to make these materials. That's really what I'm looking for, is the desire. To be completely honest, I don't even look at GPAs. I don't look at transcripts. I look at what the student says in their application, and if that desire is there, they're more than welcome to join my lab. So I accept as many students as I can during the semester. So during the semester, students do research for credit, and I'll take any student that wants to be in the lab during the semester. However, when it comes to the summer, we're limited by our internal funding as well as external funding. So then, I have to be a little bit more selective when it comes down to who can do the summer research.
Great, thank you. So we are coming up at the end of our event. This will be our last question. When you collect GSG from the plasma, how do you keep the graphene segments from sticking to each other?
Yeah, that's a very, very, very interesting question, because they don't stick to each other. Gordon Krause and I published the paper on lubricating properties of oils, but graphene itself is inherently crumpled. The graphene that we make with my plasma reactor. And because they're inherently crumpled, they have a very hard time restacking into graphite. And that keeps them dispersed when they're in polymers and when they're in oils. And they also have these other properties. So I initially thought that this would be a disadvantage to have crumpled graphene, because all of the current knowledge on graphene-based nanocomposites say that you need large flat sheets that are capable of reinforcing the material. But we make small crumpled sheets, but yet we have this wonderful increase in properties. So that's the reason why we think that there's something transformative here that hasn't yet been discovered, is because our graphene doesn't stick to each other because they're crumpled, but yet they're still doing these amazing things.
Great, thank you. Actually, you know what? I think we do have time for one more question, if you're okay with that, Albert.
No, it's all good. Always happy to answer questions.
Is it easy or possible for students themselves to raise research questions or do individual projects?
Oh yes, definitely. When students are doing the research on their own, and they come to like, I've had students come to me and said, hey, why don't we try this out? And if it's a good enough idea, I go, why not? Why don't we try it out? And we've had a few students try out their own ideas when it comes to making plasmas using RF generators. I've had students try to make graphene sponges to soak up oil, but if they have their own idea, they can certainly propose it, and we can certainly pursue it.
Awesome. So then this actually last question follows up with your last comment. What if you made Legos with GSG added in?
And that's actually a goal, right? Off the top of my head, I forgot what Legos are made out of, but we are trying to injection mold nanocomposites. So we have that injection molder. I showed that apparatus in one of my slides. The clinic program actually invested into an injection molder for our engineering curriculum. And Legos are injection molded from pellets. So that's what we're trying to do. So if you injection mold graphene with the Lego, so we envision stronger graphene or stronger Lego blocks, but Lego blocks that could potentially also conduct heat.
Very cool. Thank you. I want to thank Professor Albert Dato for joining us today and for sharing your knowledge and insights with us. Thank you to our audience for your questions and for attending this event. We will follow up within the next week with a recorded video and presentation material. An announcement for current parents: Family February is ongoing. Please visit hmc.edu/parents for the schedule of events and registration links. A weekly digest will be sent to you every Monday of all the events happening that week. All upcoming events can be found on our online offerings page using the link included in your confirmation email or by visiting alumni.hmc.edu and clicking on online offerings. We welcome any suggestions you may have for upcoming events, or if you are interested in hosting one or being one of our future speakers, please email us at alumni@hmc.edu. Thanks again for joining us and have a great night, everyone. Take care.
Bye-bye.